Significance tests ask if sample data gives convincing evidence against the null hypothesis. And that convincing evidence will be in favor of an alternative. A test answers the question, how likely is it to get a result like this just by chance if the null is true? And we answer that with a probability. So this is where we actually started the class. I'm pretty sure that this was the first lesson that we did. This idea was the first lesson. So this dot plot is a simulation of 400 sets of 50 shots of our basketball player. So this goes back to this guy who claims that he can make 80% of his free throws. So we get a sample value of 64%, and we want to know how likely it is we would get a sample value like that if he really shoots 80%. So there are 400 dots on this dot plot. Each one represents him shooting 50 times. And where the dot plot is the percent that he makes. So like his longest one is at like 82%. He had a bunch at 82. The dot plot shows the results of the simulation. Each dot on the graph represents the proportion of made shots in one set of 50. Now, hopefully you're remembering, when we look at a dot plot, this is the truth. These are the results we would get if P is true. So this dot plot is the results we would get if he really shoots 80%. You can say how strong the evidence against the player's claim is by giving the probability of your sample. So what was our sample? Well, on our picture, I had us write that he evens out around 64%. And that's what they have highlighted on the graph. We get a p hat, an actual sample value of 64%. So what is our probability that our shooter would make as few as 32 out of 50 free throws? Because 32 is 64%. 64% of 50 is 32. Based on our simulation, we estimate this probability to be 3 times. There's 3 dots where he got 64 or less. So 3 out of 400. So if he really shoots 80%, we would get a sample that low or lower only 3 times out of 400. This observed statistic of p hat equal to 0.64 is so unlikely if the actual value is p equals 80, that it gives convincing evidence that the player's claim is not true. So we use the dot plot to calculate the probability of getting the sample that we got. The probability is so low, less than 1%, that this is mathematically convincing evidence that this player is not telling the truth. He does not really shoot 80%. So be sure that you understand why this evidence is convincing. There's two possibilities or two explanations for the fact that our virtual player only made 64% of his free throws. So option one is that he's telling the truth, and just by chance, a very unlikely outcome occurred. So option one is that he's really an 80% shooter and he was just having a really bad day. By chance, he just happened to not do well. Or option two is that the alternative is correct and the population proportion or the value is really less than 80. So the sample result is not a likely outcome. So option one, he's just having a real bad day. Option two is that the true percent isn't 80. Explanation one might be correct. Explanation one might be correct. The result of our random sample of 50 shots could be due to chance alone. But the probability of getting such a result is so small that we are quite confident that explanation two is right. This number that we got out of 400 simulations is so small that we go with option two, not one. When that happens, you say we reject the null and conclude the alternative. Hi. Tomorrow, like 8 is better. Yeah. Okay. Thank you. So, how do we know if we have convincing evidence? Our sample result is very unlikely. Well, we now have a name for the probability that we use to decide if a claim is true. And it's called a p-value. The null hypothesis, HO, states the claim that we are seeking evidence against. The probability that measures the strength of the evidence against the null and in favor of the alternative, HA, is called a p-value. And we've calculated p-values a lot this year already. This percent that we got right here is a p-value. This 0.0075 is a p-value. A p-value is the probability, assuming that the null is true, that p hat or x bar would take the value specified by the alternative. That's just a fancy way of saying a p-value tells me the probability I would get the sample that I got if the null is true. Small p-values, so we're right here, small p-values are evidence against the null. So evidence against HO. Because they say that the observed result is very unlikely. Not just unlikely, very unlikely to occur when HO is true. Large p-values fail to give convincing evidence against the null because they say that the observed result is likely enough. It's still going to be a small percent. So likely enough is more like plausible. One thing to notice is that the language here, when the p-value is large, is that you fail to reject. It's not that it supports the null. We're never looking for evidence that supports the null. We always look for evidence against, and if we don't find it, that doesn't mean that we support the null. That means that we fail to reject. Okay, this makes a lot more sense once you actually see an example. So, calcium is a vital nutrient for healthy bones and teeth. The National Institute of Health recommends a calcium intake of 1,300 milligrams per day for teenagers. The NIH is concerned that teenagers aren't getting enough calcium. Researchers want to perform a test of. Okay, so the values that I am getting is 1,300 milligrams, which is a very big number. And they're saying the concern is that teenagers aren't getting enough. So the claim is that mu equals 1,300 milligrams. That's what we're testing. Are teenagers really getting 1,300 milligrams a day? The alternative is that it's really less than that, because we're concerned they aren't getting enough. Then they define the parameter for you, where mu is the mean daily calcium intake in the population of teenagers. They ask a random sample of 20 teens to record their food and drink consumption for 1 day. The researchers then compute the calcium intake for each student and get an average intake of 1,198 milligrams and a standard deviation of 411. They run a hypothesis test. So we haven't learned how to do this yet, but they run a hypothesis test and get a p-value of 14.04%. So our p-value is 0.1404. So the first question says, explain what it would mean for the null hypothesis to be true. Well, the null, being 1,300 milligrams, says that the mean daily calcium intake in the population of teenagers is 1,300 milligrams. So if this is true, teenagers are getting enough calcium. So explain what it would mean for the null to be true. Teenagers are getting enough calcium. Now they want us to interpret the p-value. So if the mean daily calcium intake in the teen population is 1,300. So if teens are really getting 1,300 milligrams a day, there is a 0.1404 or 14.04% chance of getting a sample mean as low as 1198, just by chance. So the chances we would get a sample value as low as we did is about 14% if kids are really getting the necessary amount. So this is just recapping and making clear what p-values are. P-values are calculated assuming that the null is true. So the probability comes from the null being true. And it tells you the probability that you would get the sample value that you got if the null is true. So if kids are getting enough calcium, the chances we would get a sample average as low as 1,200 is about 14%. So one good piece of news from these 2 pages is that we are now going to move away from using the dot plot to calculate our p-value. So we're not going to have to worry about anymore, do I have to count the dots to the left or to the right? We now are going to be able to actually calculate the p-value without this. So then the last thing to address is, how do we know if the p-value is too low? How do we know if the p-value is too low? So in a nutshell, our conclusion in a significance test comes down to, if the p-value is small, reject. If the p-value is large, fail to reject. So a lot of people just memorize the phrase, if the p-value is low, reject the hoe. If the p-value is low, reject the hoe. That's the easiest way to remember it. There is no rule. There is no rule for how small a p-value is required to be in order to reject. It's a matter of judgment and depends on the specific circumstances. But we can compare the p-value with a fixed value that we regard as decisive, and this is called the significance level. The significance level is denoted by the Greek letter alpha. And we have actually been working with a significance level all year. So often when we do problems like this, I say, what's our benchmark to say we have convincing evidence? And that benchmark has always been 5%. So we are used to using an alpha of 5%. Most of the time, the problem will tell you what your alpha is. If it doesn't tell you, you always use 5%. So when we assign our alpha, our fixed significance level, We reject the null when the p-value is less than alpha. So that's what we mean by when the p-value is low, reject the HO. When the p-value is lower than alpha, you reject. So in our case, this has always been if our percent is less than 5%, we have convincing evidence against. If it's greater than or equal to alpha, you fail to reject. You fail to reject. So now it's going to let us practice on a specific problem. A company has developed a new deluxe AAA battery that is supposed to last longer than its regular AAA battery. However, these new batteries are more expensive to produce, so the company would like to be convinced that they really do last longer. Based on years of experience, the company knows that its regular AAA batteries last for 30 hours of continuous use on average. The company selects an SRS of 15 new batteries and uses them continuously until they are completely drained. They get a mean lifetime of 33.9 hours. So they perform a significance test with the hypotheses. So they tell us that these batteries that they have been using or producing are 30 hours on average. So the fact that this number is big with this word average says to me that we're looking at mu. And we use the value that we know is true, well, has been true, which is 30 hours. We think and we're hoping that these batteries last more than 30 hours. So, supposed to last longer. So we're testing a null of 30 against an alternative that it's greater than 30. Then they define that mu is the true mean lifetime of the new batteries. The resulting p-value is 7.29%. So if the batteries have a 30-hour lifetime, the chances we would get a sample average of almost 34 hours is 7%. So it says, what conclusion would you make for the following significance levels? The first one is that alpha is 10%. So 10% compared to 7%. Well, 7% is lower than 10. If the p-value is low, you reject. So because the p-value of 0.729 is less than 10%, we reject the null. So we're saying the smallest our chance can be is 10%. And this one is even smaller. So we have to reject. We have convincing evidence that the company's deluxe AAA batteries last longer than 30 minutes on average. If our significance level is 10%, 7 is lower, so we reject. If our benchmark is 5%, the one that we've been using all year, well, our p-value is bigger this time. Alpha is lower. P-value is bigger. So because the p-value 0.0729 is greater than alpha, we fail to reject. We fail to reject. We do not have convincing evidence that the company's deluxe AAA batteries last longer than 30 hours. And then they give you a really important exam tip. So whenever you make one of these conclusions, you have to make an explicit comparison of the p-value and alpha. So I'm going to highlight that in yellow. So 1 is make an explicit comparison. 2 is make a decision about the null. So we fail to reject. And then the last thing that they want us to do is make a statement in context of the problem. We do not have convincing evidence that the batteries last longer than 30 minutes. And we'll practice this once we get into our free response.